This is a short note on solving linear system of equations in linear algebra. So we shall be talking about systems like this: 2x plus 3y minus 8z equal to 10 and 5x plus y, no z here, equal to 3.2. So that is an example of a system of linear equations in three unknowns, two equations in three unknowns. We can write it in the form of a matrix by extracting all the coefficients in this matrix, 2, 3, minus 8, etc. Here the coefficient is implied 1, no z, which means the coefficient here is 0. And we collect all the unknowns as x, y, z as a column vector and the right hand side as 10 and 3.2. So the general form is Ax equal to B. This is a matrix in general m by n. This is n by 1. This is m by 1. In this example, m is equal to 2 and n is equal to 3. So m, the number of rows, that gives you the number of equations, and n, the number of columns, that gives you the number of unknowns. The first important fact to be remembered about such a system is that the number of solutions, that is the number of possible x vectors satisfying that system, may be either 0, that is the system is inconsistent, there is no solution, inconsistent, or there could be exactly one solution, so unique solution, or there could be infinitely many solutions and no other thing is possible. Here we are always working with real numbers as our entries in the coefficient matrix as well as the set of possible values for the components of x. So let me first give you an example each of all these systems. So I will take absolutely simple examples. I will take x plus y is equal to 5. That is my first equation. And the second equation is 2x plus 2y is equal to 9. This is an example of an inconsistent system because if x plus y equals 5, 2x plus 2y has to be equal to 10. You can never get x and y satisfying both these cases. This is example of an inconsistent system. An example of a uniquely solvable system is possibly just this: 2x equal to 4. I have only one equation in one unknown and this has got unique solution, x equal to 2. So that is a very simple example. An example where there are infinitely many solutions may be like this: x plus y equal to 5. So there are infinitely many solutions. You just take any real number x and set y as 5 minus x. For example, I can take x to be 100 and y to be minus 95. I can take x to be 0.1 and y to be 4.9. So there are infinitely many possible solutions to this system. Now here is a quick proof that no other thing is possible. We have seen that this is possible, and this is possible. I am now going to show that nothing else is possible. For instance, you cannot have a linear system of equations that has got exactly two distinct solutions. To show that either this or this or this is possible, the standard technique in mathematics to prove such a thing, either or kind of thing, is to assume that this does not hold, and then to prove the third thing must hold. So let's pretend that there is a system Ax equal to B such that this does not hold, which means it is a consistent system. When I say a system is consistent, I mean it has got at least one solution, consistent, and I also assume that the number of solutions is not exactly one, so it is not unique. So it has got at least two distinct solutions. At least two distinct solutions. Then I want to show it must have infinitely many solutions. So I take two such solutions, call them x1 and x2. So remember, these are all vectors. So x1 is a vector and x2 is a vector. They are not just the component of a vector. So both of them are solutions and they are not equal. So what I will do is the following. I will define y as x1 minus x2. Now when I do that, I can easily see that ay must be equal to 0 because ax1 minus ax2, both of them are equal to b, so this has to be equal to 0. And y is a non-zero vector. So once I get this vector, I immediately get infinitely many solutions in the following way. I start with the vector x1, which is already a solution, and with it I add y. I claim this is also a solution, obviously, because if I multiply this with a from left, I get ax1 plus ay, and ax1, x1 being a solution of this is b, and ay you have already seen is 0, so that is equal to b. So a times this vector is also b, which means this is a solution to my system. Well, that is nothing very profound because this is, this is actually something different from both x1 and x2. Well, I can also make this 2 times y, then I will get the 2 out, 2 times 0 is 0, so that is also a solution. I can make it 3, that is another solution. I can make it any constant whatsoever and I will get a solution. So there are uncountably, infinitely many solutions that I can create. And remember, they are all distinct because y is a non-zero vector. So I have shown that if a system has got at least two solutions, it must have infinitely many solutions. So naturally the question is, if someone gives me a system ax equal to b and asks me to solve it, how am I going to describe all the solutions of ax equal to b? If this happens to be an inconsistent system, then definitely the set is very obviously just the empty set. There is no solution. If it happens to be uniquely solvable, there is only one solution. In that case, I can just give you that particular solution, that unique solution. What happens if there are infinitely many solutions? Can I somehow describe that infinite set? Turns out that the answer is yes, and quite nice. To understand how, we need a result. The result goes like this. Let xp be any solution of this system. So I am assuming that the system is consistent. It has got at least one solution. Because if it is inconsistent, then life is simple. We just say that there is no solution. So suppose xp, I have chosen the letter p because of some reason that will be clear in a moment. Let xp be any solution of ax equal to b. You take any other vector, and then I have the following result. This y is also a solution of the same system if and only if x minus y, xp minus y, or I would rather write it as y minus xp, p multiplied by a is the zero vector. This is a very important result, absolutely trivial to prove, which will enable us to express any solution, the set of general solution of all solutions of the system. Now, why is this result true? That is like this. I will first prove this part. Suppose y is also a solution. In that case, this is ay minus axp, which is, since it is a solution, this is b, and we already know that xp is a solution, this is also b, and you are left with 0 as required. On the other hand, if I give you this, then I am trying to show that y is a solution. That is, I am trying to show ay is equal to b. I will just write y in the following way. Y is actually, I will write it as y is xp plus y minus xp. That is just same as yp. And what is that? Axp, that is b, and a times this we have assumed is equal to 0, so it is equal to b, and that completes the proof. Pretty short proof. Thanks to this result, we have this interesting fact: if xp is any particular solution of ax equal to b, now you understand why I use the letter p. P stands for particular. Then the set of all solutions, sometimes called the general solution, is this thing. You start with xp, with it you add something which has the property that a times v is equal to 0. So think carefully that this is an immediate consequence of the result that I stated just now. Now this looks like a very big description, so people have made a shorthand for this. The set of all vectors v such that a v is equal to 0, we call that the null space of A, and we denote it by the script n of A. This is either called null space of A. It is also called the kernel of A. So the general solution is any particular solution plus the null space of the coefficient matrix. So coming back to the original question of if someone gives me a system and asks me to describe the set of all possible solutions, how do I do that in case it has got infinitely many solutions? The answer now is, because it has got infinitely many solutions, so it has got at least one solution, pick any particular solution. Then with it you add the null space of A. A vector plus a space means it is the space, it is the set of all vectors that can be represented as xp plus any arbitrary member of the null space of A. Now, how do you specify the null space of A? If you are writing a computer program, the typical output will be a basis of null space of A. Suppose the basis is like, I will give an example, v1 ... up to some vk. So in that case, you will print xp, you will print v1 to vk and say that the general answer is xp plus summation ci vi I from 1 to k, where ci's are any arbitrary real numbers. So that is the final way of describing the infinitely many solutions. It is an interesting fact that though there are quite a few arbitrary choices, like which particular solution do you take, which particular basis of the null space of A you take, still this description is always the same. So if I consider this set is invariant under the choice of the particular solution and the basis.